We naturally assume that reality is built on a solid foundation. If you take any everyday object and look closely enough, you expect the picture to get sharper, the details to become clearer, and the rules of the universe to make perfect, predictable sense. This assumption goes back 2,500 years to the Greek philosopher Democritus. He reasoned that if you keep cutting an object into smaller and smaller pieces, you must eventually hit a physical limit. He called this final, indivisible solid piece atomos. By 1808, British schoolteacher John Dalton brought this idea into the realm of science. Tracking the mass of elements during chemical reactions, Dalton concluded that all matter is constructed of tiny, indestructible spheres, with each element having its own unique, fixed properties. This solid sphere model offered tremendous comfort. It fit perfectly into the rules of classical physics. If the universe is just a massive collection of predictable, solid billiard balls, then by measuring the parts, you can accurately predict the behavior of the entire machine. But as the 19th century ended, physicists moved away from philosophical assumptions and started testing these structures with high-voltage electricity in the lab. In 1897, J.J. Thomson shattered the idea of the indivisible atom, proving you could actually break pieces of it, specifically tiny negatively charged particles. He found them using a sealed glass device called a cathode ray tube. By passing a high-voltage current through a vacuum, he observed a mysterious beam of particles that bent toward a positive magnetic plate. Because the whole atom is electrically neutral, Thomson reasoned that these negative particles, which he called electrons, must be floating in a pool of positive fluid. This became known as the plum pudding model. A few years later, physicist Ernest Rutherford tested this soupy atomic model by firing dense, positively charged alpha particles at a pure gold sheet. He expected the particles to punch right through the positive fluid, and most did, but a small fraction of them ricocheted violently backward, as if they had hit a solid wall. Rutherford realized that the atom wasn't a dense soup at all. It was almost entirely empty space. The positive charge, and almost all of the mass, was concentrated into a tiny central nucleus, with electrons locked in orbit around it, like planets circling the sun. This planetary model felt like a victory. We traded a solid sphere for a miniature solar system, keeping the universe neatly aligned with the comfortable clockwork mechanics of Isaac Newton. However, the planetary model collided with the laws of electromagnetism established by James Clerk Maxwell. Maxwell's equations proved that any charged particle in accelerated motion, like an electron constantly curving around a nucleus, must continuously emit electromagnetic radiation, and emitting radiation costs energy. As the electron loses energy, its orbit has to shrink. According to the laws of classical physics, every electron should spiral into the nucleus, destroying the atom in a trillionth of a second. The universe shouldn't exist. To save the structure of reality, physicist Niels Bohr had to throw out the classical rulebook. Bohr proposed that electrons don't orbit freely. Instead, they operate in quantized orbits, meaning they are locked into fixed, mathematically permitted energy shells. They cannot exist in the empty space between these rings. Instead of spiraling down gradually, an electron can instantly jump to a lower energy track. When it makes this drop, it releases its extra energy as a photon, a precise flash of visible light. Bohr's math perfectly matched the observed colors of light emitted by hydrogen, yet his fix required the admission that at the subatomic level, motion is not a smooth flow, but a series of discrete, instant jumps. The situation became even stranger in the 1920s. French physicist Louis de Broglie showed that matter exhibits wave-like properties. This bizarre dual wave particle nature ultimately laid the critical groundwork for the physicist Werner Heisenberg. Heisenberg realized there was a mechanical problem with simply looking at these particles. To detect an electron's location, you have to bounce a photon of light off of it and catch the reflection. But electrons are so incredibly small that the sheer force of the incoming light physically strikes the electron, instantly altering its speed and knocking it into a completely new trajectory. This gave rise to the uncertainty principle. You can calculate the exact position of an electron, or you can calculate its exact velocity, but nature makes it physically impossible to measure both at the same time. The uncertainty principle represents a physical limit of nature, rather than a flaw in our equipment. It proves that the act of observation alters the system itself, making absolute, predictable certainty mathematically impossible. In 1926, Erwin Schrödinger took this limitation and formulated a new mathematical foundation. He showed that electrons don't travel in clean planetary circles at all. Welcome to the quantum mechanical model. Instead of discrete paths, electrons exist in orbitals, or electron clouds. These clouds act as probability maps, showing the three-dimensional space where an electron is likely to be 90% of the time. Because of its wave nature, the electron is smeared out across the entire atom simultaneously. It doesn't actually exist in one specific pinpoint location until the exact moment you force it to by measuring it. For over 2,000 years, we searched for the bedrock of reality, expecting to find a solid, predictable sphere that made logical sense. What we found instead is a beautiful, shifting cloud of probability, a mathematical limit on exactly what we are allowed to know. In 1926, Erwin Schrödinger took this limitation and formulated a new mathematical foundation. He showed that electrons don't travel in clean planetary circles at all. Welcome to the quantum mechanical model. Instead of discrete paths, electrons exist in orbitals, or electron clouds. These clouds act as probability maps, showing the space where an electron is 90% likely to be. Because of its wave nature, the electron is smeared out across the atom simultaneously. It doesn't exist in one specific location until you measure it. For over 2,000 years, we searched for the bedrock of reality, expecting to find a solid, predictable sphere that made logical sense. What we found instead is a beautiful, shifting cloud of probability, a mathematical limit on exactly what we are allowed to know.